Okay, we're going to take a look at absolute value of rational numbers. This is our last topic on rational numbers before we exit this unit. So, absolute value. You've probably heard of it. It is intrinsically tied to inequalities, so that's kind of how we're going to be looking at absolute value. It's probably been just kind of a topic kind of hanging out there, but in actuality, it has to do everything with inequalities, so that's the focus we're going to be looking at. So the absolute value, which is marked with two vertical lines on either side of a number or of a symbol, is of a number x is defined as the distance from x to 0. So basically the length of a segment from 0 to x or x to 0, depending on whether x is negative or positive. So in particular, the absolute value is always going to be equal to or greater than 0, no matter what x may be, because if you want to think of it, distance can't be negative. So if distance is always a positive number, then whatever number you take the absolute value is going to be a positive result. So an absolute property of multiplication for any rational number x and y, if you take the absolute value of x times the absolute value of y, you get x times y and the absolute value of that. So using number lines, you'll want to pause the video. Go ahead and show that this is true for all cases of multiplication. So I want you to take the absolute value of minus x times the absolute value of y, so on and so forth. And using number lines prove that when you get the absolute value of x times the absolute value of y, you get the absolute value of both x and y. So when you're done with that, go ahead and start the video again and continue on. So if b is a positive number, then the set of all numbers x, so that the absolute value of x is less than b, consists of all the points of a distance less than b from 0, excluding the endpoints. Now, why was that last statement made? Why are we excluding the endpoints? Here is a diagram of what this is showing. So if you have 0 and you have picked that it has to be less than b, well, remember the mirror reflection of b is minus b, and that x has to be somewhere between b and minus b, and in this case we put it here, but it doesn't matter, it can be anywhere here. But the big question is, why is it excluding the endpoints? Why is it not exactly b, and why is it not exactly minus b? So see if you can answer that question. All right, so continuing with our diagram. So the inequality of the absolute value of x is less than b for a point x is equivalent to the fact that x satisfies both minus b is less than x, which that is true because it is to the left of x, and x is less than b, which is also true because x is to the left of b. So for this one statement here, we actually get two other facts from this. So it is standard practice to combine these two inequalities into a composite statement known as a double inequality. So we can say minus b is less than x, which is less than b. So in this case, we can just simplify this as the absolute value of x is less than b, and we know it to mean that it's this double inequality. So in interval notation, so we're going to introduce a new symbol. The absolute value of x is less than b is equivalent to the set, and this is a set containing minus b and b. So this kind of funky looking e means contained in the set of. Now notice that we're using parentheses. That means that this is an open interval because the endpoints are not included. Sets that include the endpoints are called closed intervals and are denoted by using the square brackets. And notice here it means less than or equal to. So now we are including minus b and b as part of our set. So depending on whether it is less than or whether it's less than or equal to, there is a difference between open and closed. And typically, you might have seen this in some other works, but this would be the same thing as denoting an open set or an open interval. Notice that we have an empty circle here, or empty point on minus b and b. So that means it would be less than. But if we have a closed interval or closed set, that means that minus b is included in the solution set and also b. So you might have seen some number line representations of this. All right, so associated double inequality. And again, we've just restated our equation here, but it's also very useful in middle school math and algebra. For example, we'll take an easy example here. Determine all the numbers x so that the absolute value of 6x plus 1 plus 2 is less than 5, and show them on a number line. So using our fact, we know that we can, and using multiplication, or I'm sorry, addition, we can take our plus 2 and move it to the other side of our inequality. Because again, if we say 4 plus 1 equals 5, we can also say 5 minus 1 equals 4. So if we're adding 2 here, we can add a negative 2 to move it to the other side of the equation, or in this case, the inequality. Well, when we simplify this, now we have the absolute value of 6x plus 1 is less than 3, which now is the same thing as stating our double inequality. So minus 3 is less than 6x plus 1, but which is less than 3. So here is where we get our set. So continuing on, determine all the numbers here. If here is our new set based on our fact, then we're going to tackle the left side of the inequality. So minus 3 is less than 6x plus 1. So we're just taking this inequality, and we have moved plus 1 to the other side. So now we have minus 3 plus minus 1 is less than 6x, which can be simplified to minus 4 is less than 6x. And because of the definition of multiplication, x is less than minus 6/4, or if we reduce it or simplify it, minus 3/2. So here's our first set of x solutions, is minus 3/2. When we look at the right side of the inequality, so the absolute value of 6x plus 1 is less than 3. We again move the plus 1 to the other side, which is plus a negative 1 or minus 1. Simplifying that, 3 plus a minus 1 is 2. And now x, using our definition of multiplication, 6 times 2/6 is 2, or in this case, 2/6 is 1/3. So here is our solution set. Minus 3/2 is less than x, and x is less than 1/2. So if we were going to graph this, it would be an open set or open interval between minus 3/2 and 1/3. So any of these x's here, doesn't matter where they are, there's an infinite amount, but it can't be less than minus 3/2 and it can't be more than 1/3 in order to satisfy this equation or inequality. All right, let's take a look at another example. Determine all the numbers x so that the absolute value of 2x minus 1/2 is greater than or equal to 3. So again, this can be written as a double inequality. So if it is greater than or equal to 3, then the other side because of the absolute value is the fact that now we have a range between -3 and 3. And again, we handle them separately. So the left side of the inequality is -3 is greater than or equal to 2x minus 1/2. And as we simplify or isolate the x so we can find out what the value is, if we're adding a minus 1/2 here, then we would add a 1/2. That would make that -5/2 is greater than or equal to 2x. And dividing by 2, we get -5/4 is greater than or equal to x. So here's our one solution set, or the one end of the solution. Let's take a look at the right side of the inequality. So 2x, oops, and I forgot to put the absolute value sign here, which is 2x is greater than or equal to 3 plus 1/2. Moving the minus 1/2 over to the other side is adding 1/2. So that is 2x is greater than or equal to 7/2. And dividing by 2, x would then be greater than or equal to 7/4. So now our solution set is -5/4 is greater than or equal to x, and x is greater than or equal to 7/4. So how does that look on a number line? Well, starting off with our number line, we mark where -5/4 and 7/4 are. But remember, x has to be less than or equal to. So notice what happens. Less than, remember, is to the left of -5/4. And notice because we have the equal to, it is a closed set. But it's everything to the left of -5/4. And if x is greater than or equal to 7/4, then the same thing happens here. It's 7/4, but everything to the right. So in essence, we have our x's are two sets, and it's excluding what is in between. So anything between -5/4 and 7/4 is not going to make this true. It is only the exclusion from -5/4 to the left and from 7/4 to the right. So that's another reason why inequalities are important, because sometimes you can find out which numbers are not going to work. So why bother with this? Why is this important? Well, basically, it is not possible in elementary math to give you an answer why absolute value is necessary. Where this really comes into play is when you get to calculus. Because as you noticed, you're dealing with limits. So there might be a limit as to what answers are appropriate, and also making estimates when you are dealing with limits. So there are situations where we want absolute value, which is the magnitude of the number, but we don't really need to know if it is positive or negative in this case, so that's why absolute value is helpful. So here's one example. Suppose you're trying to estimate the sum of two 3-digit whole numbers, 369 plus 177, and you're going to round to the nearest hundred. Well, the sum is 546, but if you estimated by rounding to the nearest hundredth, you would get 400 plus 200 equals 600. Okay? I mean, you can just go back and check that. Well, you can find out what your absolute error is, which is the absolute value of the difference between the estimated and the true value. So the absolute error, what is the difference, is the true value, which is the exact answer, minus the estimated value. So in this case, if we take the absolute value of 600, which was our estimate, minus the true value, which is 546, our error is 54. So let's do the same thing with these two numbers, 234 plus 420. You're going to get 200 plus 400 is 600 again. But the true value, when you add these together, is 654. So the absolute value, or absolute error here, is also 54 if you subtract the estimate from the true value. So it can be said that both of these estimates missed the true value by 54, but it doesn't matter whether it's over or under. So what we're interested is in the distance from the true value. So this absolute value provides an appropriate tool to express the error. So if we're looking for error analysis, then absolute value is what we use to determine these types of error. When you hear about stats, it's like plus or minus 2%. That's the same thing. That's the error analysis of what the data is trying to say. All right, we will talk about this more in class.